Welcome back, everybody. In this episode, we're going to try to multiply vectors. Now, you may remember in the last few episodes when we were talking about what a vector was, we talked about multiplying a vector by a scalar, but you may remember we never talked about multiplying two vectors together. And the reason is, in 3 dimensions, there isn't a way to multiply two vectors together and get a vector back that makes the algebra work the way we're used to multiplication working. But there are two kinds of multiplication which are really useful and gives us useful results, especially in physics. So the first of these is the dot product. The dot product will take two vectors and give us back a scalar. And the way we do this is kind of the most simple-minded way we could do it. You multiply each slot, each component in the vectors, and then you just add them all up. In other words, if we have a vector v1, v2, v3, and another vector w1, w2, w3, then we take the first slot in each vector, the v1 and the w1, multiply those together. Then we take the middle ones and multiply those together, then the last ones, multiply those together, then add everything up. Okay? This will give us just a plain old number, just a scalar, not a vector back. But it's a really useful kind of multiplication, even though multiplying two vectors doesn't give us a vector back, it just gives us a scalar. Here's an example. So we have 3, 7, negative 2, and we're going to dot that. So the little dot there is the way we denote this kind of multiplication with the vector 0, 4, 1. So I'd take the 3 times the 0, the 7 times the 4, the negative 2 times the 1, and add all that up. So you get 0, 28, and negative 2, which altogether turns out to be 26. And that's it. Super easy way to do the multiplication. It's much quicker than the other way we're going to have to multiply vectors together. Here's another example that's really easy to do and points out something that's important geometrically. If I take the vector 3, 0, so you also think of this as 3i, this is a vector pointing in the I direction, and we dot that with 0, 4, or you could write this as 4j. So it's a vector in the I direction and a vector in the j direction, and we dot product them together. We'll notice that we get 3 times 0 plus 4 times 0. It turns out to be 0. Right? Of course, the reason is I'm taking something that just points in the I direction and something that just points in the j direction. Those are perpendicular to each other. And we're going to see that's exactly what the dot product does. If you take things that are perpendicular to each other and do the dot product, you'll always get 0. The reason for this is another way of calculating the dot product, which we don't ever want to do it that way because it's far more complicated, is the dot product of v and w is actually equal to the norm of v times the norm of w times the cosine of theta, where theta here is the angle between the two vectors. So we would never want to use this equation to calculate the dot product, but we could do the dot product the easy way and then use that to find, say, the cosine of theta. Right? Notice what would happen, though, if v and w were perpendicular to each other. Then the angle would be pi over 2. The cosine of pi over 2 would be 0. So the dot product will always be 0 if the vectors are perpendicular to each other. Okay? That's really, really important. This is a super easy way to check if two vectors are perpendicular to each other. By the way, you may have always wondered, back when you were doing algebra, if you have the equation of a line, you want to find a line that's perpendicular to it, you do the slope, you do the negative reciprocal business. The reason that works is exactly this rule. If you actually looked at those two lines and you treated them as vectors pointing in particular directions, take the dot product, you get 0 if their slopes are negative reciprocals. Another thing that this rule gives us is, what if I took v and dotted it with itself? Then v dot w would be the norm of v times the norm of v times the cosine of the angle between v and v, which v and v point in the same direction, so the angle between them would be 0. Cosine of 0 is 1, so you don't see the cosine part. You just see the norm of v times the norm of v. So v dot v is the norm of v squared. You can actually get that from the formula too. It's pretty easy to see. That's a useful fact that we'll use again later. Also, it's not too hard to see that this multiplication commutes. In other words, v dot w is the same as w dot v. It doesn't matter which order you do it in. And one more bit of what looks like normal algebra also works. If you take two vectors and add them together, say v and w, and then dot them with u, you get the same thing as if you had dotted u and v together, then dotted u and w together, and added them together. So it looks almost like you can distribute, right? Like you can distribute the u across. It's not exactly what we're doing because we're not exactly doing normal multiplication. In fact, v plus w, right, is actually a vector, right? So if you look at the plus symbol here, v plus w, I'm adding two vectors, right? So this plus means vector addition. On the other hand, on the right hand side of the equation, u dot v is a scalar. U dot w is a scalar. So this plus sign means adding two scalars together. Okay, well, typical thing if you look at old final exams from Cal 2, there's very often a question like this. Find the angle between two vectors, right? So we have a vector 3, 7, negative 2 and a vector 0, 4, 1, and we want to find the angle between them. So we use the dot product to do this, right? What we need to know is the norm of each vector. So that's easy to calculate, right? For the first one, square each component, add them all together, and take the square root. So we get the square root of 62 is the norm of the first vector. Second vector is a little easier. The numbers are nicer. Is 0 squared plus 4 squared plus 1 squared is 17. So the square root of 17 is the length of the other vector. If we dot product these two vectors together, well, that's 26. We did that earlier. So now what we know is the dot product of the two vectors, the 26, should equal to the norm of each vector, right, times each other, times the cosine of the angle between them. So 26 is equal to the square root of 62 times the square root of 17 times the cosine of the angle between the two vectors. So I just take the two square roots to the other side, and I get that the angle between them has to be the inverse cosine of 26 over the square root of 62 times the square root of 17. By the way, on an exam, if you had to do this, of course, you wouldn't have a calculator. And so, how do I find the inverse cosine of this ugly number? You just leave it like that. That's a perfectly good answer, right? You don't have to try to find the cosine of some ugly angle. You just have to leave it as an inverse cosine of whatever it is. Another thing that the dot product lets us do is vector projection. So with the animation here on the screen, I think I can show what a projection looks like much better than I could if I were drawing this on a board. So here's a vector v, and here's a vector w. And what I want to do is project v onto w. I want to see how much of v points in the w direction. In other words, it literally looks like projection. So I'm going to put a sun up here in the sky, right? Bright, shiny, flashing sun. And then look at the shadow that v makes in the w direction. So if I go drop a line perpendicular straight down to w, and I try to find that shadow that v makes in the w direction, that's the projection of v in the w direction. Here's our notation for that would be projection subscript with the w to say I'm projecting in the w direction the vector v. Now, okay, I said this was supposed to be easy. It didn't look easy when I pulled up this formula. That is the norm of v times the cosine of theta times w over the norm of what? Okay, let's back off and analyze what this really says. So why the w over norm of w first? Well, that's a unit vector that points in the w direction. Because remember, if I take a vector and multiply by 1 over its length, again, I don't really want to use the word divide, right? But if I take w over the norm of w, that's going to be a unit vector that points in the w direction. So that gets my w part. Then all I have to do is find the length of my black vector, and that will give me the magnitude part. So when I multiply that by my unit vector that gives me the direction, that will give me my black vector shadow projection thing. Okay, so why does the norm of v times cosine of theta, why is that the length of my shadow? Well, remember, the cosine of theta, right, is the opposite over the adjacent over the hypotenuse, right? If I think of this as a right triangle, which of course it is because I'm projecting, see, straight down. There's my right angle. So if I'm looking at this angle between V and W, cosine of that angle is what? The adjacent side, that's the length of the black arrow that I want, divided by the hypotenuse, the length of V, right? So in other words, cosine theta is what I'm looking for divided by length of V. So if I multiply by length of V, it gives me the length of the black arrow that I'm looking for. Then I multiply that by my unit vector that gives me the direction. That's my arrow, my vector, the projection of V in the W direction. Well, we can simplify this a little bit, right? We haven't used a dot product yet, and we could, because if I look at V dot W, remember that's the norm of V times the norm of W times the cosine of theta. That's almost what I have, right? I just need an extra norm of W. So if I put that in and then divide by it, then I could use the norm of W, the norm of V, and the cosine theta to give me the dot product of V and W. I can simplify this even a little bit more because the norm of W times the norm of W is just W dot W. So, wow, that's really easy. Dot products are super easy to calculate. So if I want to find the projection of V in the W direction, it's V dot W over W dot W. Right? Remember, that's a scalar. Right? And I multiply that times the W vector. Right? The component of W in the V direction is just the length of that black arrow. Okay? That's how long that arrow is. And of course, if you check, that's just V dot W divided by the norm of W. Well, this lets us do a little bit of physics, right? So if you remember from earlier in the course, we spent a very long time talking about work, right? And work was force times distance back then, right? Actually, to be more precise, it was force in the direction that we were moving. So when we pumped water out of a tank, remember that the only force that mattered was force that was in the direction of the motion. In other words, force of gravity as we moved the water up and down. Moving the water left and right out of a pipe didn't count because it was only the force that was being applied in the direction or opposite the direction that we were moving. Well, if we have something that's not just one dimensional, something where we have vectors involved, if we have a force vector, call it F, that moves a particle along a displacement vector, call that D, then what's work? Well, it's the component of the force time in the D direction times the length of that D vector. And if you untangle using the formulas we had on the last screen, what all that says, it says that work is, well, again, it looks like force times distance, but the times means dot. Work is force, the force vector, dot, the displacement vector. So here's an example. Suppose we have a force. It's given by the vector 4, 5, 3 in newtons, and it moves a particle from one point to another, from the point 5, negative 10, 0 to the point 15, 10, and 0. Well, our force vector, we know that's 4, 5, 3 in newtons. Our displacement vector, okay, where did that 10, 20, 0 comes from? Well, that's the vector from the first point to the second point, right? That's the displacement vector. In other words, directions on how to get from 5, negative 10, 0 to 15, 10, 0. So to get from 5 to 15 in the first component, the first slot, I have to go 10. To go from negative 10 to plus 10, I have to go 20. And in the last slot, to go from 0 to 0, I go 0. So that gives me a force. I have a displacement vector d. So the work is just the dot product of the two, which turns out to be 140 joules. So I like this because this way we've gotten to go sort of full circle, right? All the way back to stuff we were doing at the very beginning with integrals and breaking things up into pieces and so forth. But now we've extended our story so that we're not just doing things in one dimension. We're doing things, that have 3 different directions that things can move. Now, you might ask yourself, what happens if the force is changing or the distance is changing as we move along? That's a great question. And that's a question for Calculus 3. So in that case, we'll get integrals again, and integrals show back up in the story. But those will come into play later when we start doing integrals that involve vectors. In fact, you might ask why we're doing vectors at all in Calculus 2, because this is really the kind of thing we'll do in Calculus 3. We just sort of introduce this and then stop. The reason is most people have seen vectors, and so it's super easy to just tack this on at the end of Calculus 2. And again, if you haven't and you have questions, then definitely email me, contact me, and I'll be glad to help and get you caught up and up to speed here. But the other reason is this acts as kind of a pre-review, right before you jump into Calculus 3. Again, for lots of people, Calculus 3 is much easier than Calculus 2 because we do the same sort of stuff you do in Calculus 1 just with vectors. But if you had to review all of dot products and cross products and stuff at the beginning of Calculus 3, then that adds on a lot of extra time and review that would be better spent diving straight into the more complicated material. So that's why this gets stuck at the end of Calculus 2. Partly to act as sort of a pre-review before Calculus 3, and partly to give us a break after we've had to deal with the really, really hard stuff we've dealt with already in Calculus 2. This lets us sort of end on an easier note.